part 5 of my series on the Lucas-Lehmer Primality test. Today we are going to be finishing our proof of the smaller theorem that we need to prove the Lucas-Lehmer Primality test. This theorem deals with groups. It's called Lagrange's theorem. I'm probably not pronouncing that right. So if you remember in last video, we talked about how we defined this qual symbol, and we said that if A equals B, then B equals A. And then we also said that any element A equals itself, right? And so today what we're going to prove is if A equals B and B equals C, then A equals C. Okay, so let's get started. So I've tried something slightly new. I decided to try to write down some of it before, so I wouldn't have to like write so much. So A, if A equals B, then that means A is equal to B times H1, right? Sorted by the definition for some H1 in H. Similarly, if B equals C, then B is equal to C times H2 for some different or possibly same H in the group H. Okay, so now because of this, what we're first, okay, so because we know what B is, C times H2, we substituted it, right? Okay, so now we have C times H2 times H1 is equal to A, right? Okay, so now what we have is because of the associativity where the parentheses don't matter, I can multiply these two first and then multiply by C. So we get H2 times H1 times C. But H2 and H1 are both elements of H, so when I multiply them by the definition of a group, and because H is a group, it must be another element in H. I will call that element right here H3. So therefore, C times some element in H, H3 is A, which by the definition I defined up here, means that C equals A, and yeah. And A equals C. I'm not gonna like when I because they're interchangeable now that we proved that if it's this way you can flip them around. Like for an equal sign, you can write 2 times 5 is 10 or 10 equals 2 times 5. It doesn't matter. So we proved that property for this. At the beginning we cannot just assume that, but we proved it, so now we know it's true. So yeah, and so therefore we have A equals C, C equals A, or yeah. Okay, so our next thing, so let me just write that down. Okay, so this implies this. Okay, so therefore, our next thing that we're going to do is going to basically, we're going to define equivalence classes. What this means is we take, so we have all the elements in G, right? And I write them all down, right? So we're going to divide them into different groups, okay? And each group, any two elements in the same group are going to be, they're going to, it means that they are qual, okay? And then any two elements, note that I do not have to specify if the first one is qual with the second or vice versa because as we proved they're equivalent. So therefore, what we have is that, so we're going to divide them into classes called equivalence classes. If they're the same, that means they're qual. If they're not, it means they're not qual. And what we're going to show is the number of elements in each equivalence class. Remember, that just means that all the elements in it are qual. Is equal to the number of elements in H. And because G has all been split up really nicely, that means that therefore G is equal to the number of elements in H times the number of equivalence classes, right? So therefore G is H, the number of elements in G is the number of elements in H times some number. So therefore the number of elements in G is divisible by the number of elements in H, which is what we're trying to prove. So let's get started with that. So let me think. Okay, so first of all, if we imagine, let's prove you can construct equivalence classes. If we imagine sort of like taking an element, right, and looking, let's see what elements, what other elements are like have this property that are qual to it. So say we have an element. Since I've used the letters A, B, and C, I'm going to use another letter. So say we have an element K, okay? And we want to see which elements in G, because K is an element of G, and we want to see which other elements in G are qual to K. Okay. So that's what we're going to try to figure out. So, for instance, well, and this is a really cool part in my opinion. So here I'll just show you my little okay. Alright. So what happens now is we look at the definition of qual. So this is our definition. Just look right at that. A is qual to B if and only if A equals B times H1 for some H in the group H. So we want to figure out what is qual to K. Okay. So let's say we want to figure out, right, K is qual to what? Or sorry, no, let's say what is qual to K. It doesn't really matter, but if we're going to use the definition, it's a lot easier, I think. So we want to figure out what things are qual to K. Okay. What? Well, by definition, it means that those things are K times H, times some H for something in the group H. So it means the things that are qual to K, they're qual if and only if there are K times one of the elements in H. Okay? And so therefore, what that means is because there's H elements in H, what that necessarily means is that there's going to be H different things qual to K. Okay? And those are all going to form an equivalence group. And I can repeat this with any K. And as such, this may be a little confusing, but basically, the general idea, I don't completely understand it, but I get the general gist of it. There may be some slight technicalities that are a little confusing. But, alright. So, you basically, because we have that each element is connected to, H other elements, right? Wait. Well, actually, it's connected to H elements total. One of those is itself, so it forms sort of a group. But then what we know is groups can't like intersect and merge because of our properties about if one's equal to another, then like if it doesn't make sense because if you have this element and it has a bunch of elements and you have this other element which generates a bunch of elements and two of those are equal because of our property about if A equals B and B equals C then A equals C, you can sort of make a travel to the second group which was never included in the first one, so it wouldn't make sense. So therefore, we can divide it into groups of size h, and therefore, the Lagrange's theorem is proven that the order or the number of elements in group G is divisible by the number of elements in group H, which is our goal for this video. So therefore, this video is finished. Thank you for watching. Goodbye.